We are discussing eigenvalues based on Rao Bhim Chapter 8. Today's topic is extremely important for learning linear algebra. We have already seen this diagram in this video lecture series before. This says that if you have a linear transformation, then you can represent it using a matrix, but only after you have fixed some basis. As a result, the properties of the matrix is actually a mixture of the properties of the linear transformation and the properties of the arbitrarily chosen basis. Now, in linear algebra, we usually care about only those properties of a matrix that are properties of the underlying linear transformations and not of the chosen basis. We have also seen that if we keep the linear transformation fixed and then just change the basis, then the matrix changes in a special way. If for some basis this matrix was A, then when you change the basis, the matrix will be of the form PA P inverse, where P is some non-singular matrix. The particular P will depend on the particular change of basis that we have used. And conversely, if we are given any non-singular P, then PAP inverse will represent the same linear transformation with respect to a suitable basis. Thus, this transformation from A to PAP inverse is very important in linear algebra, and it has a special name, Similarity Transformation, or we say that A and this matrix are similar to each other. Thus, in linear algebra, we care about only those properties of a matrix that are invariant under similarity. That is, whenever A satisfies that property, any matrix similar to that must also that property. Now consider the set of all square matrices, say of some given order. Then similarity introduces a partition of this big set. Thus it splits it up, mutually exclusive and exhaustive, into certain subsets, such that if I take any matrix here and any matrix here in the same block, then they are similar to each other. And if I take any matrix here and any matrix here in different blocks, then they are not similar to each other. Then the properties of matrices that we are generally interested in linear algebra are really not properties of the matrices themselves, but properties of an entire block, because if the property is satisfied by this, it must be satisfied by this and every other matrix in the block as well. Now this opens up a new line of attack. Suppose we had to prove some such property for some matrix. Now if instead of proving it for that matrix, we can prove it for any other matrix in the same block, that is just equivalent. Because we know if one matrix in a block satisfies that condition, everything else in the block must also satisfy the condition. Now, if this matrix, the matrix that was given, happens to be rather complicated, and if we can find some much easier matrix in the same block for which we can do the proof, then I have essentially done the proof for the complicated matrix. Now, this is very much like working with fractions. Suppose someone wants us to work out this fraction. Then instead of directly working with 256 and 128, what we do is we reduce it to the form 1 by 2, and then this is same as half minus 1/3. We know that working with this representation is equivalent to working with that complicated representation, except that this is much easier to work with. The same idea here. If you are given a complicated thing, find something simpler which is equivalent, like half is equivalent to this big fraction, and then just work with that. There are quite a few theorems that utilizes this idea. We already had one theorem in section 8.3 of the book, namely theorem 8.3.10, which say every square matrix over the field C, that is very important for this theorem, is similar to an upper triangular matrix. Now, this makes your life a lot easy, because whenever you are trying to prove any property of a square matrix, you might just as well assume, without loss of generality, that it is an upper triangular matrix. Now, upper triangular matrices are quite easy to work with. And just as a quick reminder, remember that an upper triangular matrix is one where the strict lower diagonal half is 0. The diagonal entries may or may not be 0. Here I have may or may not be 0, but this part must be 0. So if you are trying to prove that that some property which is invariant under similarity, then you can as well assume that your matrix is given to be upper triangular. Just as an example of use of this result, you can try to prove that sum of eigenvalues is equal to its trace. You will just say, let's assume without loss of generality that it is an upper triangular matrix. For an upper triangular matrix, I know that the eigenvalues are precisely its diagonal entries. So this is nothing but sum of the diagonal entries, and that is equal to trace. So for an upper triangular matrix, the result is just trivial, and thanks to this theorem, so the proof works for any square matrix. Similarly, you can see that the product of all eigenvalues must be equal to determinant. That also has a very easy proof from this theorem. The proof of this fact will be induction on n. If I take n equal to 1, then this result is of course trivial, because then it is just a scalar, and a scalar is itself an upper triangular matrix. So I will assume that this result holds up to 1 to up something k minus 1, and I want to prove it for n equal to k. Now, since I am working over the complex field, I know that there are n eigenvalues. Just pick any one of them, and then you can write AV equal to lambda V, where V is one eigenvector and lambda is an eigenvalue and V is a non-zero vector. What I shall do is that I shall extend this non-zero vector into a full basis of Cn, and then stack all these vectors together to form a matrix P, whose first column is V, second column is V2, etc. up to Vn. Then this matrix is of size n by n and is clearly non-singular. Now I shall multiply this matrix from the left by A. Now we know when I multiply a matrix by some another matrix from left, effectively this matrix will multiply each of the columns separately. So this is same as A times V, A times V2, dot 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 up to A times Vn. Of course, I do not have any information on this, but I know A times V is lambda V. Therefore, this is equal to lambda V. Then I leave these things just unchanged. Now remember that I have a change of basis in my mind, and I am working with the basis P here. So I want to express each of these vectors in terms of my basis vectors in P. In other words, I am trying to write it as P times whatever. Now the first vector is very easy to express, because I can see that my first vector in P is V itself, and it is just lambda times that. So the coefficients will be lambda, then 0, 0, all the way up to 0. Now these things I have no control on, so they will be just something. So I will just write them just as something. Now in order to see the structure, I will just split up this entire something into two parts. Suppose I call this part, say W, it is a row vector, and this part as some B. So just understand that I have done nothing here except the fact saying that all these things can be expressed as linear combinations of my basis vectors. Since I have no structure, I have said some W and some B. But the first one clearly is only a multiple of the first basis vector. So I have AP equal to this thing. So AP is equal to this. So what I do is I take my P on this side and then I can write P inverse AP is this. Observe that I have moved one step towards my goal. P inverse AP, well, I have not been able to make it upper triangular, but at least I have shaven these things off. So it is lambda, then some B. Now here I am going to use my induction hypothesis, because B is of size 1 less. So I assume that it is now K by K, or yeah, K by K. And now this one is K minus 1 by K minus 1. So by induction hypothesis, this itself can be expressed suitably as an upper triangular matrix together with two inverses on both sides. So let us say that for some Q, non-singular, Q inverse BQ is upper triangular, the name is D. Now if that is the case, all that I have to do is to multiply here by Q inverse and here by Q, and I'll be through. The only thing is that I must leave this lambda unaltered, or these zeros unaltered. Now the matrix which will do this, keep this lambda unaltered, but multiply this by Q inverse and Q, can be seen quite easily to be this matrix. So I will just define a matrix called P2, which is 1, 0, 0, and here I will put Q. Then I start with this and pre-multiply by P2 inverse, post-multiply by P2. The effect is leave lambda same and you multiply this by this. As a result, it changes to something, I do not care what it is, but this becomes 0 and this becomes D. D being an upper triangular matrix, this entire thing is an upper triangular matrix. And I have already got hold of these and these. This is a non-singular matrix and it is its inverse. So I have proved that even this A is similar to an upper triangular matrix, and that completes the proof. Thus the result was, for all square matrix A, there is a non-singular matrix P such that P inverse P is upper triangular. Now this might be generalized or slightly modified. There is nothing special about upper triangular. The way we did the induction, it will work for lower triangular just as well, or you might say just work with the transpose. That's number one. And number two is that, in fact, you can see that the way I got the non-singular matrix was by extending a non-zero vector to a basis. Now, if you just start with a V equal to lambda V, where V has unit length, this is equal to 1, then you might as well extend it to an orthonormal basis, ONB. And the same result will hold by induction. So in this case, you can also assume that not just non-singular but orthogonal. Well, we do not really call it orthogonal. When we work over the complex field, we call it unitary, which is basically same as orthogonal, except that we are working over the complex field. We can get an unitary P such that P inverse AP is lower triangular or upper triangular, whichever you like. And since it is P or it's unitary, you might as well put a transpose, or not transpose, but P star here. They're all equivalent. Now in this form, this is a very powerful form because this subsumes the non-singular case. Unitary is anyway non-singular. It is a very, very useful result, and it is called Schur decomposition. Coming back to our equivalence relationship or the similarity transform, here was the set of all square matrices, and each block consisted of all matrices that are similar to each other. This result basically shows that the set of all upper triangular matrices is something like this. There is at least one upper triangular matrix in every single block. So if you are trying to prove anything about any square matrix, anything that is invariant under similarity transform, you can, without loss of generality, assume that you are working with that particular thing, with that particular structure, namely upper triangular. Now let us consider the set of all diagonal matrices. We know that diagonal matrices are very good as well. Diagonal matrices, they lie something like this. Notice that they do not intersect all the blocks. But there are certain blocks that they do intersect, and you can guess that if I ask you to prove anything about this block, you would naturally first pick a diagonal matrix which is similar and then work with the diagonal matrix, because diagonal matrices are great. Diagonal matrices commute when they multiply. You can very easily find out their eigenvalues, eigenvectors, and you can invert them very easily. They are wonderful objects. Of course, if you were to prove something here, then you do not have the luxury of choosing a diagonal matrix that is similar to it, but for these special things, it will be great. Now, all matrices which lie in blocks that are touched by this diagonal matrix set is called semi-simple, or sometimes it is called diagonalizable. Our Rao Bhim book brings up a term called diagonable, which is not at all standard. They just made up their own terms. So semi-simple is a standard term, and it is quite well justified because symmetric, because diagonal matrices are really simple objects, so it is semi-simple, very much like a diagonal matrix. So proving something for a semi-simple matrix is essentially proving the same thing for a diagonal matrix and saying, since it is semi-simple, it must be in the same block, hence the result holds. Naturally, it is of great interest to know when a matrix is semi-simple. That is, when a matrix satisfies this relationship. This is the matrix A that we have to work with. If we can somehow show that it is similar to some diagonal matrix, we will be very happy. Now, just to rewrite this, and you will see something interesting. It is AP is PD. Now, what does that mean? Consider P as its constituent columns. So, first column, second column, etc., the last column, and then P here again the same matrix, first column, second column, the last column, and D consists of one number here, another here, another here, another here, etc. Now when you do the multiplication, you will see what is the first column here. It is A times the first column. What is the first column here? Everything is a linear combination of these, and you have only this number which is possibly non-zero, everything else is zero. So it is just this scalar times this vector. So if I call this first vector v1, I have a v1 equal to, I'll give it a name, suppose I call it lambda 1, then it is lambda 1 v1. Think about it for a moment. You will immediately see that this is nothing but that eigenvector-eigenvalue relationship, because v1 cannot be 0, it being the column of a non-singular matrix. Similarly, if we look at the second one, you will see it is v2 lambda 2 v2 when I call this thing lambda 2. In other words, this basically says that all the columns of P are nothing but eigenvectors of A corresponding to eigenvalues which are all arranged as diagonal entries of D. Is it always possible? Well, we know that there are n eigenvalues if A is n by n, but can I say that if I stack corresponding eigenvectors side by side, they will form a non-singular matrix? Oh no, that is not necessarily true, because we know that there are matrices that are not similar to diagonal. So you immediately get the first characterization of semisimple matrices. A matrix A is semisimple if and only if it is possible to have a basis of the entire space Cn, or it could be Rn, depending on whether you are working with real or complex field, consisting of only eigenvectors. Now suppose the eigenvalues of A are lambda 1 to lambda k, and I have shown only the distinct eigenvalues. Then corresponding to each of them, you have eigenspace. So from these eigenspaces, from the first one, you might get vectors like v11 to vn11. So n1 is the geometric multiplicity of lambda 1 for A. That is the dimension of the space of lambda 1 corresponding to A. So this is for lambda 1 A. So these are all linearly independent eigenvectors. Similarly, here also you can get V2 1 to Vn2 2. Now these are linearly independent, these are linearly independent. Since lambda 1 is not equal to lambda 2, the entire thing is linearly independent. So you get n1 plus n2. And similarly, you go on like this. Finally, you get Vk1 to Vknk. So that is the best that you can do. What is the size of this linearly independent set? That is exactly n1 plus n2 plus up to nk, which means it is summation of all the geometric multiplicities I from 1 to k. In order to get a basis of entire Cn, this number should be equal to n. Then you can reach the entire thing. Is there any guarantee? Well, not really, because GMs are all less than or equal to AMs. We know that the algebraic multiplicities, they indeed add up to n. Algebraic multiplicities indeed add up to n because we know that the characteristic polynomial is like this: lambda 1 to the power some m1 dot 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 lambda minus lambda k to the power mk. That is the characteristic polynomial of A, and since this must have degree equal to n, we must have summation mi equal to n. That is, algebraic multiplicities will definitely add up to n, but geometric multiplicities are less than or equal to algebraic multiplicities. So in general, all that you can say is that this will be less than or equal to n. So you get another characterization that this condition holds if and only if the sum of all the geometric multiplicities is equal to n, where lambda 1 to lambda k are all the distinct eigenvalues of A. And as GMs are always an upper bound algebraic multiplicities, and algebraic multiplicities do indeed add up to n, you have another characterization if and only if for all eigenvalue lambda you have GM lambda must be equal to algebraic multiplicity of lambda with respect to A. So each one of them must hit the ceiling, because if one of them is less than the ceiling, then they cannot add up to entire n, because the total here is already n. So if there is a little deficiency in one place, no other eigenvalue can make up that deficiency. So these things are of great importance, by which you can quickly recognize if some particular matrix is semisimple or not. Let's take some examples. Suppose you have some particular matrix for which you notice that algebraic multiplicity of all its eigenvalue is equal to 1 for all eigenvalues. Then you can immediately say that the geometric multiplicity, which is less than or equal to algebraic multiplicity, and geometric multiplicity can never be 0, so geometric multiplicity must be equal to algebraic multiplicity. So this implies that it must be semisimple. So these things are a necessary sufficient condition, but this is only a sufficient condition. This motivates defining an eigenvalue to be simple if its algebraic multiplicity equals 1. And similarly, if this condition holds, we call such an eigenvalue regular. That is, geometric multiplicity equals algebraic multiplicity. So this may be expressed by saying a matrix is semisimple if and only if all its eigenvalues are regular. Sometimes, however, it is easier to prove that a given matrix is semisimple directly from the definition. Suppose the matrix A is idempotent. Then it is quite straightforward to prove that this has to be a semisimple matrix. Just remember that such a matrix is going to be like a projection. So that is the fact that we have to use. So it is like this, that I have a screen onto which I am projecting. It need not be orthogonal projection. So I have my rays, sun rays, coming possibly in a slant way. So if I take any vector, then the shadow that I am casting is the projection. So if this is my x, then this is my AX. That is a characterization of idempotent matrices, and indeed that is why idempotent matrices are useful. Now, whenever someone gives you an idempotent matrix, I shall think of it as a projection, which means I have been given a screen, which is a subspace, and a direction of sun ray, which is t, and I have S direct sum t equal to Rn. Again, I could have used Rn or Cn, doesn't matter. So I have this thing. And if I take any vector here, in that case, any vector may be split up uniquely as one part inside S and the remaining part inside T. This split up is unique. Then mapping V to Vs is what is affected by this matrix, that is Vs equal to A times V. In this diagram, if this is my V, then this is my Vs, and this is my Vt. So Vs plus Vt makes up my V. Vs lies on the screen and Vt lies along the sun rays, so Vt is casting no shadow. So with this understanding, it is quite easy to find out the particular P which will convert this to a diagonal matrix. All that you do is this: you basically take any basis. Just take any basis of the screen. So you take any basis, I will call that V1 dot 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 up to say Vn1. That's a basis of S of the screen space. So I'm assuming that N1 is the dimension of S. Now you take any basis Vn1 plus 1, or I will just call it W1 to Wn2, that is a basis of T. That's for this thing. So if I put them together, I get a basis of the entire space, because these things are all linearly independent of these things because of this direct sum relationship. Now just observe that all these things must be eigenvectors, because if I try to project this, since it already lies on my screen, its projection will be itself. So AV1 must be equal to V1. So it is not only an eigenvector, but eigenvector with eigenvalue 1. Similarly for all this. These are also eigenvectors, because if I multiply this with A, because all these things are lying along sun rays, all these vectors, so they will cast the shadow equal to just 0. So all these things are also eigenvalues, but corresponding to eigenvectors corresponding to eigenvalue 0. So I can directly see that all these things are eigenvectors and they make a basis. So immediately I see that I can actually have this as a semisimple matrix. Not only that, I can explicitly write down the form. So the P that I'll be working with is precisely this. I will take all the V's first and all the W's then here. So I have a n by 1 non-singular matrix. Then P inverse P will be all the eigenvalues listed here. All the first n1 eigenvalues are 1, 1, 1, 1, 1, hence this identity, and these are all zeros, and anyway it's a diagonal, so these are anyway zeros. So I can see that an idempotent matrix is not just semisimple, it is semisimple in a particularly simple way. Now this form is particularly well suited. You can see that this form is available for any matrix, not necessarily just for idempotent matrix. The only thing is that you have to just put whatever eigenvalues you have. Suppose you have got some eigenvalues which are non-zero and lesser zeros, so just write them in this way. So for all the non-zero eigenvalues, the eigenvectors that you have, put them first, and the eigenvectors corresponding to the zero eigenvalues, put them last, and you can get this form for any matrix which is semisimple, not necessarily idempotent. If it is idempotent, this also happens to be the identity matrix. So this is an interesting fact, which is also one of the theorems. So in this video, I am not writing down the numbers of all the theorems because I am arriving at the theorems through very intuitive discussion. Now, semisimple matrices are very nice. We can see that. So the matrices that are not semisimple, people sometimes get angry with them, and there is a term to denote them. They are sometimes called deficient matrices. So a pejorative term which says that they are bad, that many intuitive things do not work well. So if someone asks you to prove anything about a semisimple matrix, remember the simple thing. Just prove that result for diagonal matrices and then say, because it is semisimple, the same result will hold. Just make sure that that result is preserved under similarity transformation. Now here is one simple example. Suppose I take a matrix A, a square matrix. I do not tell you whether it is deficient or semisimple. I merely tell you it's a square matrix, say field is C. Then it has a zero eigenvalue if and only if it is singular. So an eigenvalue 0 if and only if A is singular. And this naturally leads many people to speculate that there's got to be a result which says that number of non-zero eigenvalue is equal to rank. So number of non-zero eigenvalue is equal to its rank of A. Is that true? Well, it turns out that this result is not true in general, but it is true in case of semisimple matrices. Now, how do you prove it? You will say, well, since it is semisimple and I can see eigenvalues are preserved under similarity transform and so is rank, so it is as well to prove it only for diagonal matrices. Now for diagonal matrices, it is just straightforward because eigenvalues are the diagonal entries. So if you have got something like 1, 2, 0, 0 in this diagonal matrix, you can easily see that these two things are linearly independent and they are completely zero columns, so rank is equal to 2. So for diagonal matrices, it is trivial, and immediately you say that this result holds for any semi-simple matrix. Now, how do you know that it does not hold in general for all square matrices? You should now work with some deficient matrix. Now, for this, it's a good idea to have a plentiful supply of deficient matrices for counter examples. Now, here is a good source of deficient matrices. You create them like this. Just remember that since they are square matrices, so they are, of course, similar to some upper triangular matrix. So I will give you an upper triangular matrix. Just do this. You take any number. Say I will take 1, 1, 1, 1, 1, 1, 1. Fill them up with 1. Put a 0 here. Now I need to put something else here. So I know it is not going to be a diagonal matrix. So I need to put some non-zero stuff here. Do the following. Over in the super diagonal entry, keep on putting 1s. This matrix, and put just zeros here. This matrix is bound to be a deficient matrix. The simplest example being 1, 1, 1, 0. So whenever you have in mind any such result and you want to check whether this is true for something or false for something, you can try out on these matrices. You can very easily check that 1 here has algebraic multiplicity 2, but geometric multiplicity only 1, meaning that it is not semi-simple. Now coming back to that question, whether the number of non-zero eigenvalues is indeed equal to rank, of course there is no reason to put only 1 here. You can put just any other thing. You can put some lambda, lambda, lambda. That will also do. So I will put 0 here. So here is another thing, 0, 0, 1, 0. Number of non-zero eigenvalue, you can easily see, is 0 because both the eigenvalues are 0, but its rank is not 0. It's not the 0 matrix. Its rank is 1. So this shows that for deficient matrices, that result, which is a natural result, is not true, but it is true for semi-simple matrices.